Hi. So we're going to continue our discussion of competitive equilibria with one period arrow securities trading, sequential trading. So we're going to have sequential trading as we've done before. So there's going to be frequent trading. We're going to have frequent trading of a small number of commodities rather than once and for all time zero trading of very many commodities, as we did with time zero trading with Arrow DeBrew trade securities. Okay, so I prepared a Jupyter notebook to so we could go through and actually compute some things. So today I'm going to talk about actually how we'll go about computing all of the objects in a competitive equilibrium with one period arrow securities, where we've set things up so we can Bellmanize things. And so the kind of thing is this theme of this is arrow meets Markov. That's where we're going. Okay, so I'll supply this notebook. So here's the deal. There's going to be a Markov process. Everybody's endowments are going to be a function of the same Markov state. We're going to have complete markets in one period arrow securities. We're going to have discounted expected utility, sort of macro style, macro finance style. We're going to have, everybody's going to have the same preferences. You know, you could relax that at certain points in the code that I'll show you, but we're not going to. There's going to be common beliefs. So there's going to be things that are going to be generated by a Markov chain, a P and a pi zero, transition matrix, and an initial probability mass function. And everybody's going to share that, everybody inside the model, and we, the model builders. So that's what we mean by common. There's going to be, everybody's going to have the same one period utility function, and it's going to be a power function, constant relative risk aversion utility function, and everybody's going to have that. And we're going to rig this up so so that's going to imply this is going to be important, and it's going to imply something called Gorman aggregation. This is what this is going to deliver us to us, and we are going to use that to simplify computing things in some problems. We're going to have diverse allocations. People are going to have different allocations, and that's going to provide motivations for reallocating goods across. Reallocating goods, what does that mean? Across time and across Markov states. That's the whole idea of trade in this pure exchange economy. So we're going to impose enough restrictions so that we can Bellmanize. We're going to write down Bellman equations over and over again. All I mean by a Bellman equation is something that says a value function of something today consists of a payoff function today plus some kind of expected value, maybe discounted, of a value function tomorrow. That's what I mean by a Bellman equation. So we're going to use Bellman equations to compute a bunch of things that we need to in a narrow securities market. First, we're going to have asset prices. We're going to be able to compute asset prices. And this is kind of one of the big outputs. This is going to be an output of the model. The reason finance and macro guys, one good reason finance and macro guys like these models is it provides a theory of asset prices and how they co-vary with important quantities in an economy. So we'll see a version of that. Another thing we're going to use, we're going to write a Bellman equation, value functions for continuation wealth. We're going to need that because we want to find out portfolios, portfolio choices. We're going to need state-by-state natural debt limits. We're going to have to compute those and know what they are in order to pose individuals' problems. We've talked about that before. In order to pose well-posed optimum problems with a finite objective function. And we've seen that if we don't have these natural debt limits state by state, technically an equilibrium is not going to exist. Because individuals are going to all try to do the same thing, which is take advantage of Ponzi schemes, and the whole thing will not fit together. That's what I mean by an equilibrium won't exist. Okay, so kind of as a sideshow here, and for our purposes, this is a sideshow. I've written things to compute things in Python. So if you know a little Python, or you want to, actually, you could use this as a vehicle for learning Python. What this thing is here, it's a cell in a Jupyter notebook, and these are two cells in a Jupyter notebook to get started. I'll make this Jupyter notebook, which is a way a lot of scientists, physical and biological sciences, are using Jupyter notebooks now to do their communication, research, idea sketching, and that's what I've done. Okay, so when Jupyter notebooks allow you to mix code, which you'll see me doing in these cells, and text, your notes. So here we go back to text. So I want to begin with this is kind of a 5-minute description of Markov asset pricing, introduction and summary of a lot of asset pricing machinery that we've touched on a little bit, but you're equipped to. So we need some infrastructure. So infrastructure is we're going to have some Markov states, 1 through n, and they're governed by a Markov chain, where Pij are our transition probabilities of going from state I this period to state j next period, where the state we're in is a random variable that lives in this time invariant state space. So now the way we're gonna set this up is, since this is asset pricing, so this is how asset pricing theory would go in a Markov setting. We're gonna have a collection of assets. These are going to be n by 1 vectors. There's going to be k assets, numbered 1 through k, because I want to price a whole bunch of things simultaneously, that they're gonna pay off different amounts in Markov states. So what dk of s is, it's the payoff, think of d for dividend, of the kth asset in Markov state s. If you want, you could just think of k equals 1, so there's only one asset, but almost no cost of having a set of assets. Okay, so we have these assets. So then we're going to have an n by n pricing kernel. We're going to call this a pricing kernel P is a transition matrix, Q is a pricing kernel. And the way we read this is Qij is the price at time t when we're in state st equals Si. Should be in the st equals Si. When we're in state I at st of 1 unit of consumption when next period state is Sj at time t plus 1. So Qij is the price in state I today of buying 1 unit of consumption, state contingent on state J at time t plus 1. That's what this is. So we're gonna organize all these prices into an n by n matrix. That's what Q is. Now, here's something fun. The price, we could ask, okay, so suppose we're in state I today and we want to buy a risk-free, we want to buy 1 unit of consumption tomorrow for sure. So how much would that cost us? Well, all we have to do is sum over J. We're going to buy 1 unit in all J states, in all states from 1 to n. And this is the price today of 1 unit of consumption for sure. So that's the price of a risk-free 1-period bond. So then the gross rate of return on a 1-period risk-free bond is just its reciprocal. So this is the gross risk-free return today in state I. That's what that is. Okay, so just because what we're doing here is an introduction to asset pricing theory, I'm gonna pretend, I'm just gonna take, as I'm free to do, I'm gonna take this pricing kernel as exogenous. Even though the theme of what we're gonna be talking about today is it's gonna be endogenous and we're gonna determine it. But temporarily, I'm gonna take it as exogenous as a vehicle for just showing you a few of the properties of Markov asset pricing. Also, in applied work, often it is taken as exogenous. That just means determined outside the model that we're building right now. So here's 2 examples of here's 2 leading examples of a pricing kernel. One is Q equals beta. That's a discount factor times P. So beta is a constant. So so what this says is what that tells you is the price today in state I of 1 unit of consumption in state J is just beta multiplied by the probabilities. So beta is about discounting. Beta is discounting for the future. The PIJs, you could say they're quote unquote discounting for remote probabilities. So that's one model that's often used. Milton Friedman used it a lot. We'll come back to that. So here's another model. Q is equal to SP. P is my so this is an alternative model. Q is equal to SP. P is my transition matrix. S is just another square matrix. And it has a name. Stochastic discount factors. And above here, this thing up here is a special case in which we set S equal beta times the identity matrix. That's what this is. But here we're just going to set it equal to an arbitrary n by n matrix that's going to capture attitudes about different states that are different just from discounting for the future, discounting in some other way. So a lot of what we're going to do today is you could think of our model is it's going to be what we're going to do later, starting in about 3 minutes. It's going to be, I'm going to erase this because I need some room. We're going to go after, you could think of an endogenize, we're going to endogenize S, the stochastic discount factor, because that's what the general equilibrium model does. It's going to endogenize that stochastic discount factor. Okay, to conclude our asset pricing story, let's do Markov asset pricing in a nutshell for two types of assets. So there's two classical types of assets. One is a cum dividend stock. What's a cum dividend stock? So here's the deal. What a cum dividend stock does is you buy the stock today, and what do you get today? You get the dividend today, and then tomorrow, that's what you get today, and tomorrow you get the right to sell the asset before the dividend's paid. And we're going to make the price of the asset tomorrow, we're going to make a guess that it's a random variable that's a function of the Markov state. So we have the price today, it's going to be some function, and it's going to equal, what's it going to equal? We can work this out. I'll write this down. Here goes. P of S, I'll write it like this just to be compact. Price today in state I, it's going to be equal to the dividend today when I'm in state I. There's going to be one of these for each I. Plus, what about tomorrow? Well, tomorrow I'm going to be in state J, and I can sell it before the dividend comes. What's that worth? Well, I'm in state I today, so 1 unit I have to multiply by my pricing kernel and sum over J. So this is my price, this is my formula, and that holds for I equals 1 through n. So if I stack this up, I get P equals D plus QP, and that implies that I minus QP is equal to D, and that implies this formula, that P equals I minus Q inverse D. So that's my price for a cum dividend stock. Finance guys also talk about ex-dividend stocks, and the deal there is actually there's a this isn't right. I'm gonna have to fix this. Well, since it's wrong, let's fix it right now. What's the ex-dividend stock? So don't look at that. Price of an ex-dividend stock is, what do you get? You buy the stock now, and what do you get? Well, you don't get the dividend until tomorrow. You get a dividend tomorrow. That's tomorrow, and then what you do is you can sell the asset tomorrow. So it looks like this. But I have to wait till tomorrow, so I have to multiply this by Qij and sum over J. Let's go step at a time. Price today is equal to summation that. So let's work this out over here. I get P, that's a vector now, is equal to Q, okay, D plus QP. I just multiplied that out, if you'll notice. And so went from 1 to n, so I stack those up into this vector, and now I get I minus QP is equal to QD, and finally I get P equals I minus Q inverse QD. So that's the price of a ex-dividend stock. Okay. Now what we're going to do next is we're going to apply this this machinery to actually, the way to think of it is let's build a general equilibrium model in which we get Q is endogenous. What forces determine Q? That's where we're going to go.